Welcome to Lecture 9. This week we're going to finish our study of using the Laplace transform to solve differential equations. And you will note from the bottom left that I have only 26 slides today. Today's lesson is going to be a short lesson because the topics are quite tricky. If you can understand the topic straight away during the lesson, then well done to you. We're going to talk about ordinary differential equations with discontinuous forcing functions, and then we will talk about the convolution integral. First, ODEs with discontinuous forcing functions. Up to now, our forcing function, that's our function g of t on the right of the equal sign, has always been a continuous function, but that's not always going to be true in engineering. In engineering, imagine that you have a machine and you can switch the machine on or off. So in terms of our differential equations, we'd expect the input function, that's the function g of t, to be a discontinuous function. Let's suppose our machine is off for the first 10 seconds, and then we switch our machine on. So our input is 1 for another 10 seconds, and then we switch the machine off again. What would we expect the machine to do? Well, the machine is going to do nothing for the first 10 seconds because the machine is off. After we switch the machine on, the machine will quickly spin up and then start working at full power. And then when we switch it off, it will spool down and again do nothing. But it's not going to discontinuously jump from being off to being on. It's going to curve up something like this picture. That's the motivation for this section. So let's suppose we wanted to solve this initial value problem. Y double prime plus 4y is equal to a function of t which is piecewise defined. This is actually a continuous function, but it's not a smooth function. It's not differentiable. We have a function which is 0 for the first 5 seconds, and then it slopes up, and then it's equal to 1. And just to make this easiest, we'll have 0 initial conditions. Now, if you recall what we were talking about last week, we can write functions like this f in terms of the unit step function. The function is 0, then there's a change at 5, so it's going to be something u5, then there's another change at 10, so it's going to be something at u10. And at each one of these changes, or each one of these jumps, we do function on the right minus a function on the left. So we could write our function as 1 over 5, u5 of t multiplied by t minus 5 minus u10 of t multiplied by t minus 10. How do we solve an initial value problem like this? The first thing we do is we take the Laplace transform of the differential equation. And there's 2 formulae we're going to want. Let me remind you that the Laplace transform of the function t is 1 over s squared. And let me remind you of this shifting formula that we were talking a lot about in the last lesson. The Laplace transform of uc of t multiplied by f of t minus c is e to the power minus cs multiplied by capital F of s. And looking at our differential equation, we have the same number here, 5 and 5 in the first part, and in the second part we have 10 and 10. So we can use our shifting formula on each one of these components. So if we take the Laplace transform out of our differential equation, putting in the initial value conditions as 0, I leave this for you to check. We get s squared plus 4 capital Y on the left, and on the right we get 1 over 5 e to the power minus 5s minus e to the power minus 10s, all divided by s squared. You should be able to do that by now. divide both sides by s squared plus 4, and we get our equation for capital Y. If we can find the inverse Laplace transform of capital Y, then we have the solution to the initial value problem. So what do we do when we have something like this? What we do is, first we want to ignore all of the exponential functions. So we're just going to suppose that e to the power minus 5s is not here. We're going to suppose that e to the power minus 10s is not here. Let's just suppose we have the number 1 on the top. And just to make this a little bit easier, we'll forget about the 1 over 5 for now. We can put that in later easily. So let's talk about the function 1 divided by s squared over s squared plus 4. Let's give this a name. Let's call this capital H. But then capital Y is 1 over 5, e to the power minus 5s capital H, minus 1 over 5, e to the power minus 10s capital H. But remember the shifting formula in terms of H. The shifting formula said to be the Laplace transform of UC, H at t minus e is e to the power minus cs capital H. And that's sort of what we have here. We have an exponential function multiplied by capital H and another exponential function multiplied by capital H. Taking the inverse Laplace transform on both sides, UC H at t minus e is the inverse Laplace transform of e to the power minus cs capital H. If we can find small h, then we can find small y using this shifting formula. So how do we find small h? Partial fractions. I'll leave it for you to check that if we use partial fractions, we can write that capital H is 1/4 over s squared minus 1/4 over s squared plus 4. So a small h is going to be 1/4 inverse Laplace transform 1 over s squared. And then in the second term, I need an extra factor of 2 in here. I have a 4 on the bottom, so I need a 2 on the top. Square root of 4 is 2. And then the other numbers give me 1 over 8 on the outside. Check your table of elementary Laplace transforms. The inverse Laplace transform of 1 over s squared is just t. And the inverse Laplace transform of 2 over s squared plus 4 is sine 2t. So now we found small h, now we can find small y. Again, I've written the shifting formula at the top. Small y must be 1 over 5, u5 of t, small h at t minus 5, minus 1 over 5, u10 of t, h at t minus 10. And then we're ready to write down the answer. We know small h, we can substitute that in, and we can replace t by t minus 5 or t minus 10. And we get this. I'm now taking the 5 inside. So instead of t over 4, replace the t by t minus 5 on the top, multiply 4 by 5 to give 20. And then just here, previously I had 1 over 10 sine 2t. Replace the t by t minus 5, so we get sine of 2t minus 10. Sorry, that's wrong. It wasn't 1 over 10, was it? It was 1 over 8. 1 over 8 sine 2t it was. 8 multiplied by 5 gives the 40. And then in the second term, we're doing exactly the same, except instead of t minus 5, we're putting t minus 10 in. Let's do another one. Another differential equation with a discontinuous forcing function. Y double prime plus 3y prime plus 2y, and now our forcing function is 1 if t is between 0 and 10, and 0 if t is bigger than 10. We're going to use the initial conditions. Y of 0 is 1, y prime of 0 is equal to 0. Step 1, I want to write the function f, the forcing function, in terms of the unit step function. And in this case, it's just 1 minus u10 of t. And then step 2, take the Laplace transform of the differential equation and put in the initial conditions. This one I'm going to skip. You can check this. Check that this is what we get. Next step is to rearrange for capital Y. We need to find the inverse Laplace transform of this function. Now this is a little bit complicated, but we can make it easier by thinking about two functions. First, let's forget about the exponential function. Let's just think about s squared plus 3s plus 1 divided by s squared plus 3s plus 2. We know how to find the inverse Laplace transform function like this. And then we're going to look at the next part. Forget about the bit we've already just talked about. So forget about the first bracket. Well, now we're looking at minus e to the power minus 10s over s squared plus 3s plus 2. Let's use the trick that we did in the previous example. Anytime we see an exponential function, just replace it by the number 1. The second function we're going to be looking at is 1 divided by s squared plus 3s plus 2. So to be more precise, let's define capital G and capital H like this. These are the functions that we want to find the inverse Laplace transform of, because capital Y is capital G minus e to the power minus 10s capital H. If we can find small g and small h, then we can find small y. So how do we find the inverse Laplace transform of capital G and capital H? We use partial fractions. Again, I'm skipping the details here because I want to concentrate on the new stuff. You know how to do this. When you go back through this lesson, when you read the lecture notes, you can check that I haven't made a mistake here. Check that these are correct for me. And assuming these are correct, we know how to find the inverse Laplace transform of these. So I'll just tell you that small g and small h must be these functions. Okay, so now we know small g and small h. Now we can move on to finding small y. Because capital Y is capital G minus e to the power minus 10s capital H, we want to find this. The first part is easy. Inverse Laplace transform of capital G is just small g. What about the second term? For the second term, we're going to need to use our shifting formula. For the second term, we're going to have U10, the exponential becomes U10, and then capital H becomes small h, but we have to shift it. It's not small h of t, it's small h of t minus 10. And then we're ready to write down the answer. We know small g, we know small h. Small g we can just put here straight away. Small h we'll put here, but every t we need to replace by t minus 10. So the final answer to this problem is a half 1 plus 2 e to the power minus t minus e to the power minus 2t minus a half u10 of t 1 minus 2 e to the power minus t minus 10 plus e to the power minus 2 t minus 10. Another example. Y double prime plus 4y is equal to u pi of t minus u 3 pi of t. This is almost the example which I used in the pictures of the machine at the start. We have a forcing function which is 0, and then it's equal to 1, and then it's equal to 0. So we can imagine that we have some machine which is switched off. After pi seconds we switch it on, and then after 3 pi seconds we switch it off again. First, take the Laplace transform of the differential equation and rearrange it. We need to find the inverse Laplace transform of this equation. We need of this function. So what do? We do the trick that we've been doing before. Every time we see an exponential function, we forget about it. Pretend that e to the power minus pi s is not there, and pretend e to the power minus 3 pi s is not there. So just pretend that we have a function, that we have a number 1 on the top. Or I'm going to write, let capital H be 1 over s squared plus 4. Step 1 is to find the inverse Laplace transform of capital H. And then step 2 is to use the shifting formula to find small y. So first, capital H we can write in terms of partial fractions. That's a quarter multiplied by 1 over s minus a quarter multiplied by s over s squared plus 4. But that's just a quarter multiplied by the Laplace transform of 1 minus a quarter multiplied by the Laplace transform of cos 2t. So we can write down small h. I know I'm going quickly on this part. You should be able to do this. You should be able to do this part yourself by now. But if you rewatch this or read it, you can spend more time checking this. So now I know small h. The next step is to try to find small y. I want the inverse Laplace transform of e to the power minus pi s, capital H, minus the inverse Laplace transform of e to the power minus 3 pi s, capital H. It's time to use the shifting formula. That's the same as u pi, h at t minus pi, minus u 3 pi, h at t minus 3 pi. Put in h and replace t by t minus pi or t minus 3 pi, and we get our answer. That's a quarter u pi multiplied by 1 minus cos 2t minus 2 pi minus a quarter u 3 pi multiplied by 1 minus cos 2t minus 6 pi. Okay. That's the end of section 4.5. One key idea here is to use the shifting formula to introduce a new function capital H, or if we need a function capital G, find the inverse Laplace transform of those functions and then use the shifting formula to get the answer that you want. The second key idea for this week's lesson is the convolution integral. Let's suppose we have two piecewise continuous functions, f and g. We can combine them into something called the convolution of f and g. And we write this as f star g. And what this means is the integral from 0 to t, f of tau, g of t minus tau d tau. This is the Greek letter tau, but this is a dummy variable. You could use any letter here. So if you wanted to write z, z, and z, that would be okay. Let me quickly run through some properties of convolution. F convoluted with g is always the same as g convoluted with f. F convoluted with g plus h is always the same as f convoluted with g plus f convoluted with h. The third one, if you have three functions, it doesn't matter which order you do, you convolute them in. F convoluted with g convoluted h is the same as f convoluted with g convoluted with h. And then the fourth one, if one of the functions is 0, then their convolution is 0. For example, let's do cos convoluted with 1. The definition is at the top. That's the integral between 0 and t. First function as a function of tau, and then second function as a function of t minus tau d tau. Integral of cos is sine. We get sine of t minus sine of 0, but sine of 0 is 0, so that's just sine of t. Now let's do the convolution of 1 and cos. Now the theorem says it should be the same, so we should also get sine t. Integral between 0 and t. First function is a function of tau, so that's just the 1. Second function is a function of t minus tau, so cos of t minus tau d tau. And when we calculate this integral, we do get sine t again. Now, from this example, note that in general, f convoluted with 1 is not the same as f. Cos convoluted with 1 is not cos. Another example, I want to calculate sine convoluted with sine. So I'm doing the integral between 0 and t, sine tau, sine of t minus tau d tau. Sine of t minus tau is just sine t, cos tau minus cos t, sine tau. When we're integrating with respect to tau, t is a constant, so sine t and cos t could be taken outside of the integral. We have the integral of sine tau cos tau and the integral of sine squared tau. But we know how to do these. we did these in calculus. I get a half sine t1 minus cos squared t minus a half cos t minus sine t cos t. And this will simplify to a half sine t minus t over 2 cos t. Now, from this example, note that f convoluted with f is not always positive. I have a half sine t. Sine t is sometimes positive, sometimes negative. And I have minus t over 2 cos t. Cos t is sometimes positive, sometimes negative. Sine convoluted with sine is sometimes positive, sometimes it's negative. Don't fall into the trap that this is somehow sine t squared. Okay, so that's what a convolution is, but why do we study convolution in our chapter about the Laplace transform? Because of this very important theorem. The Laplace transform of f convoluted with g is capital F multiplied by capital G. So let me draw rectangles around this because this is so important to us. Now, of course, this means that if we're trying to find the inverse Laplace transform of the product of two functions, f multiplied by g, the answer is just f convoluted with g. So, for example, if we wanted to find the inverse Laplace transform of a divided by s squared plus a squared, we don't have to use partial fractions if we didn't want to. We could use convolutions. We have 1 over s squared multiplied by a over s squared plus a squared. We know that the Laplace transform of t is 1 over s squared, and we know that the Laplace transform of sine at is a over s squared plus a squared. So, small h is just the inverse Laplace transform of 1 over s squared convoluted with the inverse Laplace transform of a over s squared plus a squared. It's just t convoluted with sine at, or integral from 0 to t, tau sine a t minus tau. Calculate this integral and we get our answer. So now that's two ways to find the inverse Laplace transform of a function like this. You could either use partial fractions or you can use the convolution integral. Solve y double prime plus 4y is equal to g of t with the initial conditions y of 0 is 3, y prime of 0 is equal to minus 1. Now, this is different from what we've been looking at before because now we don't know g. G is just any function. Take the Laplace transform of the differential equation, s squared capital Y minus 3s plus 1 plus 4 capital Y is equal to capital G. And we can rearrange that to find a formula for capital Y. We need to find the inverse Laplace transform of this. Inverse Laplace transform of s over s squared plus 4, that's easy. Inverse Laplace transform of 2 over s squared plus 4, again, easy. And we need the inverse Laplace transform of 2 over s squared plus 4 capital G. For capital G, we don't know. We don't know small g, so we don't know capital G. So we use convolutions. The first two are easy, cos 2t and sin 2t. And for the third inverse Laplace transform, we have sin 2t convoluted with g. Or in terms of the integral formula at the top, we can write that the answer is 3 cos 2t minus a half sin 2t plus a half integral from 0 to t sine of 2t minus tau g tau d tau. Now there's something I've done here, which is I've swapped g and sine 2t to get the final answer. Remember, f convoluted with g is the same as g convoluted with f. So I've swapped the order and then I've put them in the formula. So this is the solution to the initial value problem for any function small g. Now I'm almost finished. I want to find the inverse Laplace transform of 2 over s minus 1 s squared plus 4. And again, I could use partial fractions if I wanted to, but I don't. I want to use the convolution integral. I want to find the inverse Laplace transform of 2 over s squared plus 4 multiplied by 1 over s minus 1. And that's just sine 2t convoluted with e to the power t. The inverse Laplace transform of 2 over s squared plus 4 is sine 2t. And the inverse Laplace transform of 1 over s minus 1 is e to the power t. So that's the integral between 0 and t, e to the power t minus tau sine of 2 tau d tau. To finish this problem, all we need to do is to calculate this integral. We can simplify it a little bit. E to the power t is a constant with respect to tau, so that can come outside the integral. We have an integration by parts integral. And I'll just tell you an antiderivative is e to the power minus tau over 5 minus sine 2 tau minus 2 cos 2 tau. Evaluate this at t and at 0, and we get our answer. I'll leave it for you to check that if you use partial fractions on this function, you can find the same answer. And then I will leave it for you to decide which method is easier. Is it easier to use partial fractions, or is it easy to calculate an integral? And then final example for today. So for y double prime plus y is equal to g of t, y of 0 is equal to 3, y prime of 0 is equal to minus 7. And again, this is for any function g of t. So we'll take the differential equation, and we will take the Laplace transform of both sides. That's 4 s squared capital Y minus s at y is 0 minus y prime is 0 plus capital Y is equal to capital G of s. We can put the initial conditions in. We can group the capital Y terms together. And then the minus 12s plus 28, we can move over to the right side. I want to take a factor of 4 out of this bracket. And then I want to divide both sides by 4 multiplied by s squared plus a quarter. Let's simplify this a little bit. 12 divided by 4 is just 3. 28 divided by 4 is just 7. And in the final bracket, look, I have a quarter on the top and I have a quarter on the bottom. The thing on the top should be the square root of the thing on the bottom. If I have a quarter on the bottom, I want to have a half on the top. So let's leave 1/2 there and take the other half away. What we have is 3 multiplied by the Laplace transform of cos t over 2 minus 14. What does this look like? That's the Laplace transform of sine t over 2. And then again, in the final bracket, we can replace a half divided by s squared plus a quarter by Laplace transform of sine t over 2. How can we find the inverse Laplace transform of the product of two functions? We use the convolutions. Three cos t over 2 minus 14 sine t over 2 plus a half small g of t convoluted with sine t over 2. And for this example, I'm going to leave the answer like this. That is the end of chapter 4, the end of today's lesson. In the final 3 lectures, we will be talking about systems of first-order linear equations. And I'll cover the first 4 sections: an introduction, the basic theory, homogeneous linear systems with constant coefficients, and then section 5.4, what do we do if we have complex eigenvalues? For the last 3 lectures of this course, we'll be using some linear algebra. So before next week's lesson, please spend a little bit of time, not a lot, just a little bit of time revising your linear algebra ideas. We need matrices, we need eigenvalues, we need determinants, etc. Diagonalization we're going to be using. So have a quick look through your linear algebra lecture notes or your linear algebra textbook and just remind yourself of that theory. Are there any questions?